welcome Maxim Zaks.
Thank you. Welcome to my talk. My name is Maxim Zaks. I'm a freelance software developer, and I would like to speak about a recent obsession of mine. I kind of like to count bytes while porting binary serialization formats to Swift. And I'm kind of doing it like last 2 years or something. So like weird obsession, but you know, you need a hobby, right? So what's going on in this talk? I will rant just a little bit about JSON. Then I will explain why binary formats are actually a better fit for lots of use cases. And then we all together will get inspired and save the world, right? Because it's something what you want to do at the end of the day, at the party, saving the world. All right, so to be honest, I actually love JSON. As far as a text-based format goes, it's actually my famous one. Like I actually once fought a really big fight to trying to get away from XML to JSON because it's much more human readable in my opinion, and so on and so forth. But there are actually parts in JSON which are like not that good, and I would like to convince you by asking you this small thing. Like you can see here, this object represents me, actually, right? It's my name, it's my birthday, so it's me, right? Well, is it a valid JSON, though? Who thinks it's valid? Only a couple, hands go up, hands go up. Who thinks it's not valid? Only a few people. Could you also tell why?
06.
Yes, thank you. So actually, this one, this little fella here, it's human readable, right? If you read it yourself, you think like, okay, 06 is 6. But in reality, and lots of parsers will take it, but the official grammar in JSON tells that it's not valid. If you have a 0, it has to be either directly terminated, or then there should be a point, and then it will be a floating number, and so on and so forth. So validity is one thing where we kind of, as humans, we just pattern matching, right? We just see something and we directly can tell like, okay, this is how it is. But another thing is actually also the size of it. If JSON is human readable, means that we have lots of white spaces, basically, and new lines and so on and so forth. So JSON, as you can see it on the screen, is actually 81 bytes. If we would minify it, and I hope you minify JSON before you send it, then it becomes 66. Like funny story, I worked for a gaming company and we had an SDK written in Objective-C which sent data from games to backend. And in this SDK, there was one part where we actually printed all JSONs before we sent them to the backend, meaning that you have a game with 2 million DAUs and you send like 2 times as much data as you actually had to. But it was just a one small flag inside of a SDK saying like, okay, printed, yes, sure, why not, right? I will present 3 binary serialization libraries today. It will be FlatBuffers, FlatBuffers, and Colfer. And here you can see how it relates from a bundle size. You see that the FlatBuffers is actually even a little bit bigger than the minified JSON. FlatBuffers is like 75%. And Colfer is actually just a third, which is cool, right? So what is Colfer? Colfer is a binary serialization format optimized for speed and size. This is what tells, this is like the sentence on the GitHub repository. And normally if I talk to people, they ask me, okay, if they hear binary serialization, they directly say protobuf. Even if people use it or don't use it, but protobuf is something which is like known by everyone and so on and so forth, and it's also baked by Google, so everyone is like protobuf. Fine. I actually wanted to not include protobuf because it would be, I didn't want it to have all free serialization protocol by Google, because FlatBuffers and FlexBuffers is also by Google. And the Colfer was actually heavily inspired by protobuf, but it's a little bit simplified with some trade-offs. However, I found it on this repository, which has a benchmark for all the serializers on Java Virtual Machine. And as you can see here, Colfer is on the first place and protobuf is over here. So I was actually intrigued to say like, interesting, what is actually different? And I will talk about it briefly. So if you have this representation of me, right, you have this name, birthday, year, month, day, how would you be able to convert it to binary, to convert it to Colfer? First thing you would need to do is actually define a schema. And with schema, you basically define types which represent those objects. So you have a person which has a name and have a birthday, and birthday is a date which has a year, month, and day. This way, when we serialize the data, we don't have to keep it in the binary itself, because from this schema, there will be a code generation step which will create classes which can access these things actually by index and not by name anymore. And this is how you can easily kind of like make things much smaller, because you're already avoiding information which is normally not needed with some code generated stuff. So here is like representation of binary, and I will just speed run through it for you, but it's actually more for the presentation afterwards. I will upload the slides, and then you can do it like slowly here. I will just rush through it, sorry. So basically how the representation is done, the first byte is basically the index of the property, it's 0. When it says the size of a string, then you get the string. Then you get to next property, which is another object, so you open up a new 0 property again, the value, first property, value, third property, value, a magic number saying we ending the object, the instance, and then we end it again. This is basically the magic. This is how it's really straightforward to serialize this kind of stuff and deserialize this kind of stuff. So there is no real parsing involved, but you still have like have to scan through the bytes and create objects out of it. Okay, and all the funkiness is actually in generated code. So there you have some bit shifting, blah, blah, blah. But as a developer, you don't have to be aware of it. You just use a very clean object-oriented API, and you are very happy about it normally. So call for all the things, right? It's actually like cool, it's fast, it's small, great. Well, I would like to talk about data serialization use cases first, because Colfer and also protobuf was designed mainly for machine-to-machine communication. So if you have two processes and you would like to kind of send a message to something remotely. And for this, you have one use case, but from my experience, you have two additional use cases where you say, I have an application state which I would like to serialize and persist, so I would be able to start a new session at some point. This is also a valid use case for data serialization, and also representation of configuration and data dumps. So meaning that for me, for example, the storyboards are configurations. They tell which UI elements are where, basically, and in this case, they can become very large. Right, so it's some kind of a data which you ship with your app, and your app at runtime will just read some parts out of it, and not necessarily the whole thing. Okay, so what are the requirements for machine-to-machine communication? First of all is the small payload, right? Because there is networking involved and you would like to have the smallest latency as possible. Then efficient encoding and decoding. On mobile, on the clients, it's actually not that important because you say like, okay, I do it off thread, and if it takes like a couple milliseconds more, it's fine. But by defining the format, you also enforce the server to use the same format. And for servers, it's actually important to have an efficient encoding and decoding because they have to handle lots of requests, lots of response. And it would be nice to have something which is actually very efficient in encoding and decoding. Then formalized typed API is actually nice. It's nice to have a contract between two communicating parties because otherwise it's very easy to run into bugs. And last but not least is actually versioning, and compatibility between different versions. So if you have like an old client and new client, it's nice if they don't crash each other. If they, like you can try to prevent them talking to each other at all, but if it's, it should happen then they should at least not crush each other and stay kind of compatible to each other. So with Culver, it's actually a small payload. We said yes, we saw that, a third of JSON, without any archiving and gzipping and so on and so forth. Efficient encoding and decoding, yes, we saw that as well. Formalized typed API, yes, you have a schema, and therefore everything is typed. Where the developer of Culver actually kind of cut an edge was actually versioning and compatibility. And with compatibility, you basically have two cases. You have one case which is backwards compatible. You have a new version, and it should be able to receive data from an older version, and it shouldn't crash. It should be able to accept it. And with new versions, for example, in our case, we had this name and birthday. Maybe I would like to add birthplace. So in the new version, I would have 3 fields, and I would like the new client still be able to communicate with someone who only knows the name and the birthday. Okay? There is another way, which is forwards compatibility, meaning that the old client can still talk to a newer client. And here is where Culver doesn't work, because if I would send an older client an object with 3 properties and not 2, it will expect an end of object at the second object property, sorry, and then it will say, oh, I don't understand what you're talking about, therefore I'm throwing an exception, and I wouldn't be able to interpret this message at all. By the way, Protobuf actually has this strategy implemented, so you can you have forwards and backwards compatibility. It's always a little bit restricted how you can evolve your schemas and so on and so forth, but generally if you keep to the rules, then it's all fine for you. Now, the question is, can we actually do better, right? So maybe there is something else which would add a little bit more value in here. And let's talk about FlatBuffers. FlatBuffers is an efficient cross-platform serialization library for games and other memory-constrained applications, and it's developed at Google. And as I said, I have this small hobby of porting stuff, so I actually ported it to Swift, which you can find then on my GitHub repository. And while porting it, after you port something, you try to benchmark it, right? And to see actually what kind of stuff can I get out of it. And also for me, it was important to compare it with C++, the kind of like the initial implementation of FlatBuffers. But actually here you can see that if you use JSON serializer, and in this test what I do, it's a smaller object tree where you have like 600 bytes or something. And if you encode it 100,000 times with JSON serializer, then you kind of have this kind of time. This is in milliseconds. If you do it with FlatBuffers, it's 12 times faster, in a way, which is already impressive, which is already good. If you do decoding, though, then you see you go from this to 17 milliseconds, which is 260, something like this. This is actually huge, right? And if you think this is huge, then let's look at second slide, which shows you the memory consumption which you get. And you can see, like, for example, with the decoding with JSON, we use more than 230 megabytes. With FlatBuffers, it's 11 kilobytes. Meaning that basically there is a zero cost of memory. Because if you think about it, you had an iteration over 100,000 times of something, and it's less than 100K. Meaning that with every iteration, you don't waste anything. It's just basically, there is a little bit of overhead, but it's for all runs and not for each run which accumulates, in a way. Okay, so if you like to use FlatBuffers, here at the left for you, you see the schema from Colfer, and here is the schema from FlatBuffers, which looks actually the same, almost. Syntactically, it's a little bit different, but there is also one difference, is basically that here we say the person is a table, and the date is a struct. FlatBuffers has a concept of, as Swift, it has a concept of value types and reference types. Meaning that value types are actually stored by offset, and, reference types are stored by offset, and value types are stored in place. So if you need to have something very fast, it's better to use structs. But if you would like to have some structure which maybe has some references and so on and so forth, then reference types is actually a good idea, and I will show a few examples where it actually makes lots of sense. So I will have a short run through again through the binary of FlatBuffers. Again, it's a little bit too much, but like bear with me. I would just briefly would like to see a few concepts from FlatBuffers. I think it helps to see them once. So in FlatBuffers, what we do is the first 4 bytes actually tell you, this is the first reference to the instance of a root table, which tells you, okay, the root table is 12 bytes ahead. Then every instance has a virtual table. So in there is another jump to the virtual table itself. Virtual table tells you how many properties you have, how big the object is itself, and then we also have, it tells you where you can find the properties. So lots of jumping around, in a way. Let's see how FlatBuffers kind of performs on this usefulness for machine-to-machine communication. So we see this payload is still small. It's smaller than JSON. It's not as small as Colfer, but you know. Efficient encoding and decoding as well, not as good as Colfer, but still, as we saw, much better than what you would get with a typical text-based. Formalized type API, yes, there is a schema. The code is generated, therefore you work against a fully typed system. And thanks to the vtable and all this jumping around, you actually have support for versioning, evaluation strategies, compatibility, and so on and so forth. However, we also can top this a little bit. And as I said, we actually have 3 use cases for serialization data, right? Machine-to-machine communication is the obvious use case, which people use a lot, but we could also persist state. And here, in my experience, the main thing which is different in persistent application state from sending a message to someone is that the application state is pretty much interconnected. Normally, it's a graph. It's not a tree, so it's not a hierarchy in a way. It can be connecting like wildly. Let's call it like this. And a year ago, I implemented an app which is sadly only in German, and it's kind of like a news bot which lives in this app. And when you receive, I also call it like a text adventure for news in a way. So you see like a message, and then you can decide if you would like to go deeper into the in this news, or you would like to get some other news. So basically, the conversation itself looks something like this. So it's a graph. You have a message, and then you can go here and exit directly, or you could say like, okay, I'm interested in this, and then this, and this. Okay? And this kind of state I could represent with, this is a simplified schema of my data state. So I have a message which has a text, which could have a URL to Giphy, URL to image, blah, 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 all kind of stuff. Then I have this called message link, which has the message and has also information like a link to all the next messages which you have. So it's basically like a representation of such node. And then the application itself is basically a history where we have just an array of scene messages, because then they were already linearized. You saw them basically as a stack. But I can at any time stop and just keep the last message link in the application state, and therefore easily just serialize these things without needing new concepts to represent it with a database or trying to do something with JSON and so on and so forth. So for me, it was like really, when I understood that I can actually use real graphs there, it was quite simple to implement quite complicated structure in a way. All right, so the last but not least is representation of configurations or data dumps. And I have, like, the main thing with huge amount of data is basically random value access is king. So if you have like megabytes of data, if you would need to kind of like convert it all into objects in your programming languages so that only there you can query them, this is pretty wasteful. If you are able to actually just read something inside of this buffer, it's actually quite good. And as we saw previously how FlatBuffers is structured, it's anyways basically a graph. You can jump around. You don't have to like completely unmarshal everything. So here's a use case which I got from, I spoke at a meetup once, and someone approached me saying like he had a problem. He needed to make an offline search for city names, and he has a huge amount of data, and he tried it with a database but had some problems with it. So if it would be possible to solve with FlatBuffers. And like I looked at it, and generally the data dump is all cities in the world. So it's a little bit over 3 million entries. You have a country code name, normalized name, and map coordinates. As CSV, it's 150 megabytes. When I transform it to FlatBuffers, it was 27 megabytes more, and I will explain why in a second. And then I defined it as a following schema. I say I have a city of lists, and it has two arrays. Cities sorted by country code, and cities sorted by name. So if you have a sorted array, basically the search becomes just a binary search, which is very efficient, right? So here's an example, and one thing which I would like to tell before. With FlatBuffer Swift, you have two options how you can access data. You can access it in the memory directly, so you would have to load everything up into the memory, and then you can access it. Or you can access it directly through a file reader. So you give it a URL and say like, okay, this is the URL to the file, and then just fetch stuff only which you actually need. Okay? So let's start the video. I will first do the memory, and I search for all the cities in Switzerland, which is 3,600 cities from 3 million, and now I will search for Luzon. And as you can see, normally every query is around 0.2 milliseconds. Now I go with a file and do the same. And here it's a little bit slower. I didn't know how to type Luzon, so I was always checking like, how do you spell this? How do you spell this? All right. So generally, what we saw is when you do it from memory, it's like 0.2 milliseconds, worst case. If you do it from file, it's 32 milliseconds, worst case, which is 100 times slower. But in this kind of use case, it's actually pretty fine. 32 milliseconds for a query, it's nothing. So it's still 30 FPS, and I actually forgot to scroll through the list, but you can scroll through it with no problem, 60 FPS, this all works fine. However, if I turn off the memory profiler, what you can see here is basically, this is the memory footprint. If I do it in memory, so if I load everything into memory directly, and then I'm very fast, but I'm wasting lots of memory. Or if I do it for files, 100 times slower, but only a fraction of memory is used in this case. All right. So why is it possible to do with FlatBuffers is basically, again, as I said, tables are reference types. So in these arrays, city by country code and city by name, I only store the reference. And it's only 4 bytes. I don't store the city. The city is stored separately. Therefore, if I would do it with JSON, for example, which supports only 3 structures, and I would really put a city twice there, then I would end up with 6 million entries. This way, I only store the references, and the data itself stored somewhere else. Meaning that actually we have like around 3 million entries, 4 bytes per reference. It's already 12 megabytes, 12 megabytes by 2, 24. So it's kind of like this 27 megabytes overhead, which I had compared to CSV files. Okay, are we done yet? Not yet. Do I have like 5 minutes? Roughly 4 minutes. Okay, I will be short. So there was one more format, right? So if you saw it in this slide, so basically we have this FlatBuffers, which is faster, still faster than JSON, but actually slower than FlatBuffers. And this is a new kid on the block. It was implemented only this year, actually, and got published by Google in the FlatBuffers project, and I also ported it already to Swift. And this one is schemaless binary encoding, meaning that the main benefits are you don't need a schema. So if you would like to be more dynamic and don't like identify the types in the beginning, then you can do this. There is no code generation needed. It's just a library, or just generally only one file. But you still have the random value access. So the values will be stored in a way that you can directly access them at runtime without unmarshalling or parsing and so on and so forth. It can easily transform JSON to FlatBuffers. I actually implemented a small custom JSON parser which directly parses JSON and puts it directly into a FlatBuffer. And it supports all the types which you have in JSON and a little bit more, and it keeps the type information in the binary. So this is an example how you would use FlexBuffers. So you say just FlexBuffers data from JSON data, and this call will just basically transform the string into the data which will be accessible through FlexBuffers. Then I can say FlexBuffers decode data, I get an accessor, and then I can query by key, basically. And then I can also do this kind of concatenating queries, which works fine. And at the end, you just have to say which type you expect. There is also a nil check. You could also like put a real nil inside of your array or object whatsoever. And you, as FlexBuffers captures the type, it can tell you, yeah, it's nil, not because I didn't understood it, but because it's actually nil. It's supposed to be a nil. Okay, Outlook. Generally, I think it's important to always focus on the use case. JSON has lots of use cases where it's perfect. But in many use cases, I think it would be better to actually look a little bit around and not just fall back to the things which we know and therefore like, okay, it's good. Like think about how many electricity we could actually like reduce when the servers stop wasting so much time at actually just parsing the request and generating response. And I believe that actually start thinking in graphs helps a lot. Because like if you think about it, we are kind of defined by the tooling that we use. If we have a tool which is naturally work with trees, you start thinking in trees. You stop thinking, saying like, okay, this is how I should do this, and this is why it's actually makes sense. But if you have a tool which will let you actually have a much superior representation of data, then I believe it can lead to much better solutions, basically. Okay? Thank you very much.